Welcome back to Chem 101. For this video, we are going to look at, orbital diagrams. Now these are very similar to electron configurations. In fact, we can use an electron configuration to get an orbital diagram. So these are atomic orbital diagrams, different from molecular orbital diagrams, which we will look at in a different video. Alright, let's start with an electron configuration. We can take carbon. Carbon has 6 electrons, and the electron configuration for carbon would be 1s2, 2s2, 2p2. So when we are writing the orbital diagram, we want to fill in these electrons, and we use arrow notation. So for the 1s, 1, and the 1s, 2 electrons. The reason that they are oppositely spinned is the pauli exclusion principle. It says that when 2 electrons go into the same subshell, they have to be of different spin. So we would do the same thing in this next orbital. And now in the 2p, we're going to go ahead and put 2 electrons in there. Now the reason we don't put the electrons into the same, both in here, for example, is because Hund's rule says, and really the Aufbau principle, when we're following the Aufbau principle that says that the electrons will go into the lowest available orbital and go, build upwards from there, Hund's rule shows us that the electrons will also avoid pairing up until they have to. So this would be the orbital diagram for carbon. Now we can build on that if we take a different element. Let's take oxygen, for example. Oxygen has 8 electrons, and so we know that this is going to be, instead of 2p2, it's going to be 2p4. And so now when we fill in our electrons, 2 in the 1s2, 2 in the 2s2, we get our 5th electron, and now by convention we will go to this first block again and put in our down electron. Really, all 3 of these energy available shells here, they're all the same energy, but so that everyone's on the same page when we're writing orbital diagrams or when we're assigning quantum numbers, we'll always fill in from left to right. Let's look at copper. Copper has 29 electrons. So remember, copper, from the last video we looked at, has an irregular electron configuration. So let's fill in copper's electrons here. 1, 2, 3, 4, 5, 6, 7, following Hund's rule. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, and 29. Something else to note about orbital diagrams is that they can usually tell us whether or not an element should have magnetic properties. If we see unpaired electrons, these are going to give us magnetic properties. Elements that have completely filled or paired electrons have non-magnetic properties. So check this out for yourself. Look at the orbital diagram for iron and notice that it has unpaired electrons, a lot of them. This does not explain all magnetic properties. Oxygen, for example, doesn't appear to have any unpaired electrons in its orbital diagram. Let me rephrase. Molecular oxygen, in its molecular orbital diagram, doesn't have any unpaired electrons, yet it does have magnetic properties. So orbital diagrams in general are not perfect, but we can always improve by looking at other theories, and we'll do that later on. So for now, unpaired electrons gives you magnetic properties. Paired electrons gives you non-magnetic properties. And in the next video, we're going to look at using orbital diagrams to now assign quantum numbers to specific electrons. I'll mention something else that I didn't say beforehand. My electron configurations is what I'm looking at when I decide how many electrons to put in each of these boxes. So if you notice, I have one electron in this 4s shell. That's why there's only one electron here. There's 10 in the 3D. That's why there's 10 here. So know your electron configurations ahead of time. This will help you decide how to put your electrons into the orbital diagrams. And what I do, I like to just write them both at the same time. You might as well. This gets practice, and practice makes perfect.